Okay, to 5.4, applying definite integration. I'll just say applications. Okay, it has specific applications in the title. I'm going to clutter it up because we're just going to go right to the areas between curves, and then we'll do average values after. Okay. If f of x, g of x are continuous on an interval a to b, but also with specifically f of x being greater than g of x, so on the graph f of x will lie above g of x. I'll draw a picture in a bit. On an interval a to b, a closed interval a to b, then the area of the region between f of x and g of x on the interval the same interval a to b. I'll write it out as an inequality. So a is your lower bound, b is your upper bound on it. I'll draw a picture in a bit. Is given by, and we're just doing a definite integral from a to b. And what we're going to be doing is we're going to be subtracting. We'll be subtracting the upper curve, the one that's higher, minus the lower curve, and that's our integrand, just the difference of those two functions. And the book uses brackets or parentheses whenever they have multiple terms in an integrand. Technically they don't need it because that caps off your integrand, but just so it's maybe readable and following the way the book writes it, I'll write it like that. Okay, and that's going to be the area between, the region between f and g on that interval. Let me draw you a little picture. Yeah, I can fit it here. Because it's going to be a rough sketch. You've got some function f, continuous, some function g. I'm just drawing some generic functions, g of x. And we're going to cap off an interval from a to b. You could go negative, but I'm going to keep it in the first quadrant to make the picture a little bit easier to understand. But the idea is we want the region between f and g from a to b. So we want that region there. And all you're going to do is make an integrand by subtracting the upper curve minus the lower curve. That's going to be a common notion in the future of upper curve minus lower curve. What was I going to say? Oh, this integral, we're not going to do it, but where did my blue pen go? Uh-oh. The way I'm just briefly going to talk about the way it works. Basically, this integral, because it's two separate terms and a difference, you could break it up into the definite integral for just f, the definite integral from a to b of g, oops, and then subtracting those two results, because you can break it up as a difference or sum of an integral. It works that way if it's a sum or difference. And what that does is it gives us the entire area under f from a to b. That first one at least. This one right here gives us that entire area. G is coming in a little bit below that, so G looks like that. And what we're doing is then we're doing the integral with respect of G from a to b. And that's going to be the area under G, so that's going to be that area there. And we're subtracting it, so we're literally going to just subtract out an area that we don't want, and leaving us with the area that's bounded by f and g. So that's the idea behind it. There's going to be one application of that in the future at the end of the section. For now, I'm just going to give you some abstract ones. I will note though, the homework doesn't really cover it, and I'm not going to really get into it because I don't want to throw too much at you. But in situations where they tell you the region bounded by f and g, and you do have to kind of get an idea of what the graph looks like so you can identify the upper and the lower curve. They often won't tell you which one's the upper one and which one's the lower, and you got to figure it out by having a general idea of what the graph will look like. And if you try to graph it and you realize that they cross they cross 3 times rather, you can't just do a single integral from a to b to capture both those regions combined. If you want the area bounded by these curves, it is a combined area of 2 of those. And the upper and lower curve switches, so even if that's a and that's b, you won't be able to do a single integral from a to b with that because your upper and lower curve switches. You will have to figure out where they cross, see, and you'll have to, let's say this piece is from f is on top, g is on the bottom. You would do it from a to c, f minus g, but then when you go to, then you got to separate out c to b, and note that now g is the upper curve, f is the lower, and you'd have to do one from c to b with these switched to cover the fact that g is now your upper. More complicated than we need to get to here, but just be conscious of that as the upper curve and lower curve you have to identify, and they could switch for more complicated problems. I don't think I gave you any of those, so we'll skip through that. Anyway, let's do an example real quick. Another thing is they're not going to necessarily give you the A and B, like I just talked about. Here I'm going to give you a problem where it says, find the area bounded by. Let me make sure I'm in frame the whole way. Yeah, we're good, but a little bit of glare. All right, find the area bounded by the curves. Y is equal to x squared plus 1. And y is equal to x plus 3. A line, a parabola, they do expect you to have some idea of what it looks like. Back in college algebra, they had you do some of the basic translations. Also note they didn't give you an A and B, just the regions bounded by. So there would probably be one situation where they close each other, they close off the region. So you're going to have to find intersection points. This is not the accurate graph, but we need to spend time making a somewhat accurate graph. So let's talk about this a little bit. This is technically a review of previous math classes, but I'm going to note that, anticipating what I'm going to need, I know it's going to actually cross into the second quadrant. That's only because I didn't know ahead of time. All right. X squared plus 1. Your graph of x squared, you're supposed to know, is a parabola passing with a vertex at the origin. This is not the graph that I'm looking at, but that's y is equal to x squared. And when you see that with just a constant added or subtracted, that's shifting it vertically, so up and down. So that's a shift up of 1. So let me draw that somewhat accurately. Your y-intercept will be 1. And it's going to be a parabola. Apart from that, I don't need to be super accurate, but I do need to know it's an upward-facing parabola. And maybe passing through 1, 0 is relevant, but the main thing is I know it's a parabola shifted up a little bit. Okay. Next, that's a line. You got to recognize that. That's a line with slope 1, y-intercept 3. So it's going to go through 1, 3. That's, sorry, 0, 3. That's 1, 2, 3. It's going to go through there. Slope 1, so it's going to go up 1 and over 1 from there. So it's going to look like this. Positive sloping line crossing the upward-facing parabola twice. And actually, let me extend that because I'm going to need to specifically, and this is the region bounded by those 2 curves. Let me make sure we know which one is which. Oops. You don't need to put the y, I mean, I can put y is equal to, but we know it's y is equal to. I'm just going to put that x plus 3 as a line right there. I'm going to label that x squared plus 1, and that is enough to tell us that x plus 3 is our f, the upper curve. G of x is the parabola, is a lower curve. Don't be fooled by the fact that this is a square. It's going to be higher. It's not in this area. So that's the region we're looking at. We're going to set up an integral of that minus that, but we do not have boundaries. We need to find them. So we will need, that boundary is going to be our a, the lower bound of our integral, and that's going to be b, the upper bound of our integral. And we need to find those. So let's do that real quick. We're going to find intersection. And if you have conveniently your functions in the form of y is equal to, then you're looking for an x and a y pair that satisfy both, meaning those y should be equal. which means we're looking for something that makes x plus 3 equal to x squared plus 1. So we're going to set the equations equal to each other, and that's how we solve our intersection point. All right, quadratic, I got x squared. I'm going to move it all to one side. I'll move it this way. I'm going to have x squared minus x minus 2. So quadratic, you get everything to one side. If necessary, you solve you apply the quadratic formula to get possibly irrational, ugly intersection points or solutions. Usually, I give you things that factor nicely, and this one does. And so we have x is equal to negative. Wait, is that right? Wait, what am I doing? Hold on. Yeah, if you caught that, good. I don't know what I'm doing. Okay. No, that was good. Because you're going to subtract the 3, right? X squared minus x minus 2. No, that was good, that was good. I have it right there too, I don't even want to look at it. Okay. X equals negative 1 and 2. So those are the x coordinates of our boundaries. That's negative 1, that's positive 2. Those are your points of intersection that'll cap off the regions. That's what we're going to use. If you want the coordinates of those points, you need to take each of those separately and plug it into either equation. They're supposed to give you the same y coordinate there. So you plug in negative 1 into there, you'll get 2. Negative 1 into there, you'll get 2 as well. So this is actually negative 1 comma 2. And I get that by plugging negative 1 into either equation. Although they both should give you the same answer. You can check by plugging in for both. Plug in 2. 2 plus 3 is 5. Plug it in there. 2 squared plus 1 is also 5. So this is 2, 5. But I actually didn't need that. The y coordinates are not things we need here, so that was a semi-waste of time. But, you know, if you need that review, that's how you would find those points of intersection, but we just wanted those boundaries of the region. So I just need negative 1 and 2. Make sure you're doing their upper curve first, minus your lower curve second. One way to tell that you did it wrong is if you get a negative value. This is supposed to give us an area. Should be positive. If you switch these, it just gives you the negative of the correct answer. So be conscious of that. Also be conscious of this fact that this minus sign here will apply to every term in G. That applies to all the terms, and you have to distribute. So that's my G of x, my lower curve, and that minus sign will apply to both that x squared and the plus 1, so I have to distribute. From there, I'm just doing an integral. I'm going to put in order as well. Negative x squared, I'll have a plus x, and I'll have a 3 minus 1, so I'll have a plus 2. That's where that 2 came from that I remember. Okay. Anyway, doesn't matter the order you put it in, but I like to put it in descending powers, and now I'm doing my power rule. I'm going to do things quickly because we've done a bunch of examples on various quizzes, so check the quizzes if you've been skipping them if you are stuck, because I did extensive examples. That's my antiderivative there. I'm going to be plugging in negative 1 and 2. I'm out of room, so I'm going to go over here. You save that if you need it, but that's how you find intersections. Okay, I'm going to go over here now. And I just got to plug in and you go out of space. Oof. Negative 1/3. I'm going to plug in my upper bound, 2. I'll put it in brackets even though it won't matter. It will matter that this is in brackets when I plug in the lower bound because that minus sign will apply to all of it. I don't have enough room. Alright, hold on. I'm going to make some room and write bigger for you. Let's get rid of all this. Alright. Yeah. Here's my antiderivative. I'm going to plug in the upper bound of 2. Then I'll plug in my lower bound of negative 1. from there. It's just a lot of arithmetic. Fractions are unavoidable at this stage, so you're going to have to deal with them, knowing when you need a common denominator and whatnot to add and subtract. I'm going to fly through this quickly because I don't want to waste time with it. Just arithmetic, just be careful. It's going to be negative 8/3. It's going to be plus 2, plus 4. And also distribute that minus sign, so I'm just going to get a bunch of terms. That's a negative 1 cubed is going to be negative, times that's going to be positive, distributing that's going to be negative. Negative 1/3. Negative 1 squared is going to be positive 1/2. Subtracting that, we'll get negative 1/2. That's a negative 2. With this minus sign, it'll become a plus 2. Alright, let me see what I got. I'll do my fractions. I'll do my whole numbers. And then I'll combine them afterwards. The fractions over here. I need a common denominator. So I need a common denominator of 6. Negative 16/6 minus 2/6 minus 3/6 plus 8. Negative 21/6. All right, I can reduce. Yeah, I can reduce it. That's negative 7/2 when I reduce it, and I need to now combine it. No, we can't leave it like that. You gotta combine it to a single fraction reduced. I need to common denominator of 2. Nine halves. And yep. So just be careful. This is very prone to errors. Lots of errors happen there. Not that big a deal. I'll probably even let it slide as long as I get this set up correctly. Just be careful, but make sure you understand the setup, what we have to do to get there. Just a region bounded by two curves. We have the intersection points. Those are our boundaries. We've got to make sure we establish which one is the upper curve and the lower curve, and then just do an antiderivative. That's usually polynomials, and it can get ugly with the computations, but yeah, again, just be careful with this. Right. I'll do another one of those on the quiz, but here we're going to move on to some other applications. So far we've just been finding areas in the curves using integration. I haven't really talked about where it's useful, so I'm going to give you a basic one. And also brush on, or touch on, what are called Riemann sums, but not doing it extensively. Okay, the annual profit, so profit per year, it's a rate of which you're earning money of company XYZ, your standard fake company for business courses. T years from now, T is going to be a variable with the right now present being T is equal to 0, the current year. What do I write? From now. From now is given by, and we're going to keep it simple. They'll give you slightly more terms and not as nice, clean functions for profit to work with. But here, to keep it simple, so you can follow along, we're just going to use P of T is equal to 2T squared. What is the total profit? Over the next 6 years, meaning from T0 to T is equal to 6. Now, the answer we're going to get simply by, what the hell was that? We're going to get the answer simply by integrating from 0 to 6 that function, but we're going to spend some time talking about why that's going to get you the total profit over the 6 years. So I'm going to draw several pictures. Pretty detailed, although maybe not completely to scale. 1, 2, 3, 4, 5, and 6, and we want the total profit over those 6 years. Our function looks like this. I'm going to scale it so it's not super steep like it actually would be. 2t squared is a very steep parabola. I'm going to flatten that or scale that down so we can see some details. Okay, and this is giving you annual profit. Meaning it's treating, so it's, even though it's given as a continuous function, so the annual profit at the end of year 1 is whatever P1 is. That's going to be actually 2. Plug in 1 there, you'll get 2. At year 3, your annual profit is going to be P of 3, which is going to be 2 times 3 squared, 18. And in between there, it's going up and up, so it's actually tracking it on an almost daily basis. But these numbers, the height of the function, is what you would make over the course of a year at that level. But that level is constantly changing. So the way we can estimate profit, well, we're going to estimate it first before we do an accurate one. So what we're going to do is we can chop off this interval into what are called sub-intervals, and we can choose however many sub-intervals we want. And to start off, I'm going to increase that to larger amounts of sub-intervals. So I'm going to do very big chunks. 3 sub-intervals. And I'm going to look at those 3 sub-intervals of equal length. So I'm going to look at this one from the first 2 years, then the next 2 years from year 2 to year 4, and then the last 2 years from year 4 to year 6. And what we're going to do is create what are called Riemann sums. They're just rectangles showing you the total an estimate of the total profit made over those sub-intervals, those 2-year spans. So the idea here is in sub-interval 1, this is 2 years. They're all 2 years, by the way. The annual profit goes from 0, and they get more profitable and more profitable. At the end of year 1, they're making about 2 million per year. Oh, this is in millions, by the way. Or thousands, I don't really care, but I definitely don't want it in dollars. I don't want $18 of profit. Millions of dollars. Sorry, let me throw it in. What is the total profit over? Okay, I just needed units. All right. Anyway, so it's increasing from making no profit at all, and they start running their business and building up their company. And at the end of year 1, they're making money at a rate that would get them 2 million per year if that rate was extended. If everything stayed steady from there on, they'd be making exactly 2 million per year. But they're still building their company up, and by the end of year 2, or by the end of year 3 rather, they're making what would get them 18 million per year. If they stayed steady at that rate from there on, it'd be 18 million per year the rest of their careers. But they're still building it up and building it up. The idea is, within that span of 2 years, the first 2 years, I want to get an estimate, or I just want to use some fixed number, some annual profit. And you can use different ones, but one of the common things to do is do the midpoint. So in the first 2 years, the midpoint of that time span is 1, and so we can use right here, this 2. We're going to pretend that over this span, they're making this constant rate of 2 million per year. And so how much are they making over that first 2 years? It's 2 mil, our estimate, per year times 2 years. So we're estimating that they made 4 million over the first 2 years. And by multiplying that, we're getting the area of this rectangle right there. Okay, moving on, because now we got 2 more sub-intervals to do. From year 2 to year 3, we can use a midpoint of that as a representative value of what annual profit you're making. So 3, right here. At the end of year 3, they're making money at a rate that would earn them 18 million in profit per year. We're going to pretend that that's a steady annual profit rate that extends for the entire span from year 2 to year 4. 18 million constant. And how much are they making there? Well, they're making 18 million and another 18 million over 2 years. So they will be making 18 million per year now is our estimate, our representative value. It's not continuous, it's not a flat 18, but we're treating it as if it is to get an estimate. Times 2 years. And so over that span of time, we're going to estimate that they made $36 million. Last one will be consistent. We'll use a midpoint of year 4 to year 6. And well, I didn't do that one. I plug in 5 into my equation. it's going to be 50. So their profitability, their annual profit, is going from whatever that is in year 4, it's going up and up, hits 50 million, keeps going up and up. But we'll treat it as if, for estimation purposes, as if they're making 50 million over that 2-year span. And so 50 million, that's just this height. The height of that rectangle is 50 times 2 years. So 50 million over that year, 50 million over that year is what we're estimating. And so that chunk is going to be $100 million. $50 million per year over 2 years is what we're going to use as an estimate of how much money they're taking in over that 2-year span. Okay, and so our total profit is approximately, I'm going to emphasize that that's a squiggle equal sign. It's an approximation because this is not accurate. The accurate one would be using the actual continuous function, but we've been using some broad estimates of their profitability over 2-year spans. But if we do that, we get 140 million. But and these are called Riemann sums. Let me throw that in. Is it IE or EI? Did I even write it down? IE, Riemann sums with 2 n's. You don't need to know that anyway. I'm just worried about misspelling that dude's name. Riemann sums with n is equal to 3 sub-intervals is what we just did. An actual thing they do in calculus to kind of get an idea. Anyway, so that's the estimate of their total profit made over that 6-year span. It's not the accurate amount, but you can see how the total amount of money that they're accumulating over that time is areas that are roughly under, or an estimate of what's under the curve. So that's how that works. I'm going to pause it because I'm going to answer this text. But obviously, I did some 3 chunks of wide intervals. It'd be better if I had done 1 year by 1 year, or even month by month by month. So the more rectangles I do, the higher I increase n, the closer it is going to be to the actual area under the curve. So pause for a second. Okay, up here I'm going to draw 2 other pictures that are based on that, but so smaller though, because I'm not going to go through as many details. But their function looks like that. Okay, so the idea when we start deriving how integration works and how it equals area and whatnot, yeah, okay. Like I said, what would have been better is if I had done it in 1-year intervals, or even half-year intervals, or quarter-year intervals, or whatever. 1, 2, 3, 4, 5. Oh, shit. Yeah, let's go. Okay, and I'm not going to go through it. It'd be the same idea. I could take this interval right there, the first year, we're going by 1-year intervals now, which means that I'm going to do n is equal to 6 sub-intervals. So I'd have 6 Riemann sums. I'd use a midpoint. I'd find 0.5. I'd plug it in. I'm not going to do it. I use that rectangle there. Year 2, I'd do the midpoint there. Find the profitability at 1.5 years. T is equal to 1.5. Use that. Use the midpoint there. And sometimes I don't even use midpoints. They could actually use what are called right endpoints and left endpoints. We're not going to get into that, but you can use any, in this interval, you can use any of these profits there, midpoint, which is a nice one to go for intuitively. And last one, midpoint, we take that at year 5.5, find the profitability there, make a rectangle. And that's going to get us a better estimate of the total profitability. It would give us, if we did all this with 6 subintervals, we would get 143 million. Still not quite there, because what we would like to do is see what happens as if you do more rectangles, like every day, every second. So you're looking at the limit as n goes to infinity of this concept of Riemann sums, which I don't have. I'm not going to go write the notation for it. It's like a summation notation of P of t star, where t is a star, like some midpoint there, times a change in t, which are the lengths of these subintervals. Here your change in t is 2. I goes from 1 to n. That's how they write it out, and they take the limit as n goes to infinity, which means you're doing smaller and smaller rectangles. We are not getting into that kind of thing, but the idea is when you take that limit, and we do have the tools to actually work out a limit like that. It ends up being the area under the curve, the exact area under the curve now. So this is still an approximation, a pretty good one. And now the way we do this would be to go 0 to 6, 2t squared dt. And when we work that out, no, let's work it out. You get you get 2/3 t cubed, 6 to 0, and you will get 144. That is the exact area under the curve. That is the exact total profit made if our profit is given by this continuous function. Okay, but anyway, all of that was just to make sure you understand how areas and curves can be applied to a situation like this where you're given a rate, an annual rate of profit, and you want to figure out the total profit made, means the accumulation of all the money that's given by the area under the curve. Well, before I move on, I did want to mention something that's relevant to today. So, a lot of the graphs you're seeing in the news lately are graphs showing the number of new cases that we're seeing of people with COVID-19. So this is not the accurate function, obviously, but if this is a number of new cases of COVID or something, this is a graph. And after, let me change it to 6 months. All right, so you plug in 6 into that function, and it shows you that you have 72 new cases. Or let's say this is thousands, 72,000. Okay. Now that's not the number of cases because that's just the number of new cases. So let me say new cases of COVID. And I've seen a lot of these. That's not the total number of cases. How you get the total number of cases is accumulating all those new cases over the first month, over the second month, over the third month, over the fourth month, over the fifth month, and around a month. Okay, but anyway, so it's the accumulation. This is just the number of new cases for that particular month, but you'd have to add all the cases that accumulated up to that point. So this would be a situation where it would be the area in the curve, so sometimes it's deceptive. Now this would not account for the fact that people do recover and develop immunity, hopefully, but the idea is just a graph of the number of new cases does not get you where we're at in total number of cases. You need to do the accumulation, and that would be an integral. So it is relevant to you analyzing that kind of thing. I'm going to do another one of those profit ones. I'm going to mention negative profit, and I mentioned it before that the integral does treat areas under the axis as negative areas. So we'll do one of these. It's going to be another example of that. I'm not doing Riemann sums. I'm going to go straight to an integral, but I do want to talk about the annual profit of a competing company. Let's say company ABC. T years from now. Is given by P of t is equal to not negative, 1 plus 4t minus t squared. It does have a negative in front of the square term. That makes it a downward facing parabola. Millions of dollars, let's say again. What is the total profit over the first 5 years? Or from now on, yeah, I'll say that. So we're just going from year 0, which is now, to 5 years later, 5 years in the future. over the next 5 years, let's say. That makes more sense. Okay, let's talk about this graph. I'm going to 5. It's going to be a downward facing parabola. I could find my intercept if I plug in p of 0. I'll do some side work. I'm just trying to get a semi-accurate graph that I don't necessarily need. I could do this problem in one shot with just a definite integral. I'm using this to make sure we can do some of the things that we haven't touched in a while. The intercept, P0, is going to be 1. So at the start, it's making about $1 million per year. That's your y-intercept. Where's your vertex? Vertex, you can do completing the square. You could do derivatives. You could find your local max. That would be the thing. Yeah, let's do that. I was going to say we could do also the negative b over 2a. Let me do that too. Okay, so be careful. This is negative t squared plus 4t plus 1 if you put it in descending power, so it's a, b, c. Ax squared plus bx plus c. Make sure you treat the a as the coefficient of the square term, the b as the coefficient of the term to the 1 power, and c as a constant term. So don't look at this as a, b, c. You got to rearrange it or mentally rearrange it. Anyway, negative b over 2a. It's going to be negative 4 over 2 times negative 1. 4! No, not 4. What am I saying? 2. 2 is where the vertex is. 1, 2, 3, 4, 5. So my vertex is going to be here at 2 comma something. If I wanted that something, I could plug in p of 2. Well, let me do it. 1 plus 8. It's going to be 9 minus 4. I believe it's 5. 5 million. Let me see. Yeah, looks like about 5. Okay. Yeah, let me scale this down a little bit. 1, 2, 3, 4, 5. So it's going to hit there. It's going to hit there. Let me also mention that I could have done it with my derivatives. I could have done p prime of t, which is going to be 4 minus 2t. Set it to be 0. Solve for t, 2. Double check that it's a local max by maybe taking the second derivative. Second derivative is negative 2, and that means when I plug in the 2 into there, I get a negative 2 second derivative. That means it's concave down there, and since it's a critical point and it's concave down there, that makes it a local mass. Just refreshing your memory about some of the things we've done in the past. Vertex we did in chapter 1, but we learned how to identify local max, which would be the vertex here, with derivatives and second derivatives. All right, but anyway, definitely 5. 2 comma 5 is my local maximum, and it's the absolute max since it's just going down like that. All right, where's it going to hit the axis? Where's my, this is my y-intercept there. Sorry, I should have labeled it. That's my vertex there. I'm disorganized, I realize that now. But anyway, x-intercepts. The way I do that is I set the function equal to 0. I'm looking for a y value of 0. I'm finding the x coordinate that gives me that. Obviously I have different variables, not x and y, but same idea. I gotta set my function equal to 0 to see where it's gonna hit the axis, where profit's gonna be 0. I have to solve this. It's a quadratic. I'm gonna move everything to one of the other side, so I get a positive t squared, a minus 4t, and a minus 1. So I'm gonna move it all that way. But I'll just put my 0 over here. So anyway, or multiply the whole thing by negative 1. No, I just didn't want a negative there. I don't like it, especially when I'm trying to factor. Can I factor? Nope. So quadratic. I've not done this. I've not emphasized it. I've tried to avoid this, but now that I got time, because I got 2 weeks and I'm almost done, let me just make sure we can find an intercept where it's not going to factor nicely. You're going to do the quadratic formula. All right, so it's going to be negative b plus or minus b squared. I'm going to fly through it, but you got to know your quadratic formula. B squared minus 4ac over 2a. It's going to be 4 plus or minus. It's going to be 16 plus 4. 20 over 2. You got to be able to reduce that. The 20 is square root of 20. If 4 is a factor of that, so that's going to be square root of 4, which is 2. It's left with a 5 that stays in the radical, and I can reduce it. It's going to be 2 plus or minus the square root of 5. Okay, let me get a calculator and get some estimates of this. Two plus square root of 5. 4.23. Okay. So right about there is 2 plus the square root of 5, which is approximately I'll just say 4.2. That's where it's going to hit. The other intercept that I get by doing the minus is going to be over here, so it's a parabola, and it would have another intercept over here in the negative side. I don't care about that. I mean, I could, but the main thing is I want to do is have an idea of the fact that it hits 0 profitability here and it goes negative there. And we are doing the total profit from year 0 to year 5. So that means we're accumulating profit, and the accumulation of profit stops there, and then we start losing money, and you have to accumulate that money lost per year. So we got to handle, well, we don't have to handle the negative area. The integral does it, but be conscious of what we're going to be doing. We're going to be doing the integral, which will add all this area, and it will subtract this area, because it's going to treat that as a negative area, even though that doesn't have a geometric interpretation. For integrals, it treats it as losing money, negative profit, over the course of not quite a full year. And we've got to account for that loss of money if we want the total profit. Anyway, none of that was necessary. Once you recognize what the problem is asking you, you literally just do 0 to 5, and it'll take care of that negative area for you. You do not even have to worry about it. I didn't even need that 4.2, to be honest with you. I was just showing you, just so to remind you. All I'm going to do is take my profit function, integrate from 0 to 5. That'll get me the total area, treating that loss of money as negative area, which is perfect because that's what I want. All right, I'm just going to do this one more time, but very quickly because I'm flying through antiderivatives. All right, I'm going to check though. That's 1/3. Okay, 0 to 5. I'm going to plug in 5. 5 squared, 5 cubed. Okay, so I plug in the 5 into that antiderivative. I'll plug in 0 into the antiderivative. If you know it's going to be 0, feel free to just ignore that part. A lot of times you're doing 0 to something, and plugging in 0 will just give you 0. Not always, so be careful. But here, this is all just 0. I don't know why I'm even writing this all out. All right. So I'm going to be doing 5 plus 50 minus 125 over 3 minus 0. What am I doing here? 5 plus 50 times 0. I feel like and I got 40 over 3? 40 over 3. What is that equal to? 13.3 million. Okay. And if I wanted to find just a profit made when it's making positive profit, I had to do it up to there. I literally used 2.5 in my derivative, but I don't want that. I want to account for the fact that I lost money in that last part of the last year. Okay, I'm going to do more different topic now. Next we're going to do average value. Next concept, the average value. The average value of a function over the interval a to b is given by, for some reason the book uses capital V for the average value. I've never seen that before, and it's confusing because we use it for other things and it's not related to the function, whatever we're doing. What I've seen in books that makes a little more sense and makes it easy to identify what function you're trying to find the average value of is to put a bar over it. But anyway, the average, but it's going to be it's not a function, it's a fixed value, so I'm not putting t because it's literally a value that's an average. The form is given by 1 over b minus a times the integral from a to b of your function. Okay, so that's your average value formula. We'll do an example and you'll understand that formula. It's not too obscure. It's definitely within our capability to understand what that formula is doing for us. Simplest thing for me to do is to use a previous function. Not the average. The annual profit. I'll use the same annual profit function. The first one. T years from now. Annual profit T for years from now, I'm going to trim down my explanation. Years from now is given by, keep writing that. P of t is equal to 2t squared. Keeping my function simple because I don't want to bog down in multiple terms and a lot of fractions as we work with this. Because I want you to more get the understanding of it. So we'll keep it a simple parabola function. What is the average annual profit over the first 6 years? Okay, so we're using that same annual profit function, which I'm going to draw. Oh, let me take a moment because I was worried about sticking with only one function. Doing the total profit for a situation like this is straightforward. You just do the definite integral. It's sometimes hard to know when the integral is appropriate for a problem. That one I did the Riemann sum, so that was kind of illustrated of it. But when we do that, I do kind of want to mention that you're doing your function p of t in here, and then we put this little dt here that as of now I've been just saying it's just a conventional notation for capping that off. That comes from, that's like the limit as n goes to infinity of those Riemann sums of a change in t, where a change in t might be a little chunk of time there. And to do annual profit, you would take the profit there and multiply it by however many years, or even if you're doing smaller values, maybe days. So profit, annual profit per year, multiplied by how much time, how many years you're talking about, even if it's less than 1. And that's where this is coming from. You're doing P of t, the profitability, the annual profit at that moment in time, times however much of a time span you want to do it. And so that's coming from that. So you're doing an integral to do something when what you're trying to do, total profit, you would get by doing annual profit times time. Another context that's more for physics is velocity. I actually had this example as velocity, but I realized I should be doing business sort of things and sticking with what the book does. But this is most commonly taught with velocity. So if you want to figure out total distance, you would do, you want to take your speed at that moment in time, like let's say you're going 10 miles per hour. And let's say this little chunk of t is you want to just go 1 hour. And so you'd be going 10 miles, so 10 miles. But if its chunk is going to be 2 hours rather, then you'd be going 10 miles per hour for 2 hours, and that means you'd be going 10 times 2, which is 20. So that's the idea, 10 miles per hour times 20. So it's whenever you want to take your function value, the height of it, and multiply it by a span of whatever this variable is. because that's what that notation is actually telling you to do. I don't want to get too much into that. It is more theoretical, but that is how to identify when you're doing an integral to get something. And this is still not going to be always obvious. It's even sometimes not obvious to me unless I really think it through. Anyway, let's go back to profitability. I'm just going to follow the formula for now, but then I'll talk about what it's doing. So your average profit, your average annual profit, because that's what P of T represents, annual profit per year, we're going to get by doing 1 over, oh sorry, I'm going to do 0 to 6. 6 minus 0, integral from 0 to 6 of 2t squared dt. That's what we're doing. I did this before. It was 144. I'm going to put units even though it's not necessary, but I do want to mention that $144 million is that integral. I'm not done because I've got to do that piece. And that's the area under the curve. The money you accumulate over 6 years is the area under that curve. For the average annual profit, oh, sorry, and let me mention that's over 6 years. I'm going to put a lot of notation. That's over 6 years. And intuitively, actually, I'm going to put this as a side thing. Well, it's basically, you're making $144 million over 6 years based on our previous work. And to do an average, without worrying about this, to do an average per year, average annual profit, you just want to take that 144 and divide by 6. You want to chop that up into 6 pieces. And that's exactly what this piece is for. You're dividing by how much time, in this case, how much time, how many years pass. So you're doing 1 over 6 years, not 1 over 6, yeah, sorry. I'm trying to figure out how to write it. I got it better that way. Okay. Alright, I'm just going to work it out first. You do your antiderivative. I'm not going to show the work again, but anyway, that integral from 0 to 6 of 2t squared dt is 144, as we talked about earlier. Divide that by 1/6. You get an answer, but let me go ahead and put it in a fraction form, and then talk about what those represent. We've got kind of just went through it earlier, but let me reorganize. That 144 represents a total of $144 million over 6 years. And to get an average annual rate, you want to divide by 6 years. So that's all it's doing. It's getting the total here and dividing by however many years you have for this particular context. I can get an answer. 24. If you want to have a nice round answer. 24 million per year. Annual profit. Okay. We're done, but I do want to do a geometrical interpretation. I think one of the homework exercises will make you do a geometric interpretation, which I'm just going to fit on here. No, I'm not. I'm going to draw another picture. Okay, so as we discussed, the total profit is given by the area. Your average profit, your average value of the function p is something millions of dollars, so it's an actual thing that's on here. 24 is our p bar, if I use that notation that I mentioned earlier. Average for a bar putting over something here. And the idea now is you would make the same amount of money if you made a profit with this function over 6 years, but you would also make the same if you just made a steady 24 million consistent over the course of those years. I think I put it too high, to be honest with you. So if you made a steady $24 million per year over 6 years, steady, you're making 24 million every year. So your total profit in that case would be, guess what it would be? 144 million, that's right. 24 million per year times 6 years would be 144 million. And so that area of that rectangle is identical to that area. So this is $144 million is represented by that area. This is giving the same area over that span in time. All right, that's the geometrical interpretation. Just a rectangle of length 6 with a height of 24 gives you an identical area as that 144. Okay, next we're going to do another application of integrals called Lorenz curve and the Gini index, which is the measure of economic inequality. I felt that of all the many applications, this one was, it's doable, and it's something that I've seen in the news in recent years. Okay, so the Lorenz curve is, is a function that's related to a particular group or society or country. They are using L of x for the Lorenz curve here that measures the proportion, which is essentially like a percent but in decimal form. So when they say like a proportion of 0.7, that's 70%. A proportion of 0.5 is 50%. So it measures the proportion of a group's wealth or income, which are different things, but they use that wealth in their definition, but then the graphs that they're using refers to incomes that is possessed by a given proportion, another proportion, of its people. So this is quantifying when they say like 1% of the top 1% owns 50% of the wealth. I don't know what figures they use, but that idea, it can be captured by a graph called a function called the Lorenz curve. So we're going to go up to 1. We'll use x there, but that is proportion, or again, that's going to be percentage in decimal form. So the 1 represents 100%. I'm going to draw this bigger. I'm going to put some details. They're going to be fake details, but they will illustrate it nonetheless. 1 representing 100%. And that's a proportion of people. Is that right? Yeah. Proportion of population. I probably shouldn't abbreviate, but I'm wrong anyway because it's too many POPs. Proportion of the population. So 10% would be there, 50% there, 100% is the 1. And then same thing here, it's going to be a proportion of wealth or income. Wealth is harder to deal with because people have savings or inheritance, but income is just, every year everybody makes a certain amount, everybody employed at least. So oftentimes they'll capture this idea with income, proportionate income. Okay, now 100% of the population has to possess 100% of the income. So that's going to be there. But the graph oftentimes will look like this. And it's commonly, or lately especially, it's been common to refer to the 99%, where the 99% and the 1%ers, how much of the income do they control, Jeff Bezos. The 99% versus 1%, I have to go like super right there. That would be represented by that. Because it's still close to 1, I'm going to back off that 99% a little bit. And I'm going to go for the 90%. So they don't usually refer to the 90% and the top 10%, but we'll do that just so we can see where it's at. So the idea is now, that means 90% of the population controls, well, based on this graph that I completely made up, I'm going to say 40%. So that means 90% of the population only controls 40% of the wealth, and that means the top 10% will control the remainder 60%. So that's the idea behind this graph. And on top of this graph, you could put what they're referring to as the line of income equality, the line of total. Sorry, I forget the word that our book uses. The complete equality line. Which, by the way, is y is equal to x. So that's the idea. If you're on this line, then 30% control 30%, the bottom 50% control 50%, and it's considered total equality, which some people consider ideal. And the further away you are from that line of complete equality, the worse income equity you have. I don't want to say it's bad, because I'm sure some people believe it's not a bad thing, but generally, when people talk about income equality as a bad thing, that's basically, it's bad when this line is way down here and then comes up like that. Oh, and I forgot to label the actual Lorenz curve. That's that right there. LMX, the Lorenz curve for a particular society. Now, that wasn't bad. I mean, I'm not saying it's good, but that's not the worst I've heard. 90% controlling only 40%. And, sorry, I'm going to change this to 0.40. You can, if 0.4 is the same thing, obviously, but I'd like to see that in 0 so I can mentally convert it to 40% a little bit easier. All right, let's look at a different country. So that's maybe one country. And they always have to dip below. They're not going to be above, which means that the poor people own a lot of the wealth, which is not possible. It's always got to be below the curve. But how far below the line of complete inequality is how much inequality you have. So a real unequal country will look like that. So let's look at the 90% now. 90%, holy smokes, they only control 10% or so. I'm going to say 10% because it dips so far below. That means 90%, the bottom 90% of earners are only earning 10% of the overall income, and that means the top 10% is taking in 90%. So that's heavy inequality. And so that's the idea behind the Lorenz curve. We're not actually going to, well, we are going to work with Lorenz curves, but we're going to use that to find what's called the Gini index. So let me go over here for the Gini index is based on this graph. And I've seen that in the news for the past 10 years, especially after the crash in 2008. Where they are looking at and all this talk about who's owning what, and Jeff Bezos and all these people in the top 1% and what they're doing. The Gini index was used to compare countries, and the U.S. has what is considered a high level of income inequality. The Gini index is a proportion of the area, so it's areas on this graph between the Lorenz curve and the complete equality line. Proportion of that area to another area, so it's going to be kind of a run-on sentence, but the proportion of the area that's in that little section, that little banana-shaped section, to the area under the equality line. Okay, so the area under the equality line is going to be this area right here, the whole thing, right below that line, so all of that. And we can do an integral for that, but notice, geometrically it's half of this square, a square of side 1, 1, and so the area of that square is 1 times 1, which is 1, and that's literally half of that area. So that area will be a fixed 1/2. That's going to be the bottom of it, so it's going to, I'm going to work this out in more detail, but we're going to basically have a 1/2 under there. Because that's the area of what they talked about in the second part of it, the area under the equality line. And on top, it's the area between the Lorentz curve and that line of inequality. So we're going to take this red banana shaped area, and it's going to go on top. And that area is going to be a area bound by two curves. Yeah, so that's what we're essentially going to do. I'm going to flesh it out a little bit more detail later, but it's just going to be the area of one section to the area of another section, and that other section, the triangle, it's just going to have an area of 1/2. Okay. Okay, so going to the line of perfect or complete equality. It's a line going to the origin, slope 1, because you're going 1 up and 1 over. So this line has the equation y is equal to x. And like I said, one of the bottom area geometrically you know is 1/2, but you could literally, I'm going to erase this after, but you could go from 0 to 1 of that function x dx to find that area. Even though we knew it geometrically, it'd be the antiderivative of that 1/2 x squared. I got to put in 1, 0. I'm going to get 1/2 times 1 squared minus 1/2 times 0 squared, and that simply confirms that that area is 1/2. So that's your bottom area. No need to actually do an integral for that. If you can just do it geometrically. So that's where the 1/2 comes from, but no need for that. The main part is that slice, the banana slice. That's all that's. So I want that area, but it's important to note the two curves. That's your upper curve, the y is equal to x. That's your lower curve, the Lorentz curve. And that's the area that I want. And so now I'm going to write the formula out. They're using capital G for this. I don't know if it's a standard thing. They're going to put 1/2 on the bottom, but that means you're going to be multiply by the reciprocal of that, so it's going to be 2 times. But let me write it out anyway. And we're going to integrate from 0 to 1. And we're going to do what we did at the start of this lecture. Upper curve, the x, minus the lower curve, whatever L of x is. I didn't give you an actual curve to work with yet, but we will in a bit. But when we do get that, that's what it will be. Well, a little bit simplifying it, that's what it will be. Just that integral region between curves times 2, because they're dividing by 1/2. And that should give you a proportion that's like a percentage that should be less than 1. Oh, wait. No, my bad. It would be greater than 1. Because that area is less than 1. Okay, let's do a couple of these. Oh, and let me just mention, sorry, bullet point. We saw there the bigger that area was, the mean it was worse equality. So to note, higher Gini index indicates greater inequality, greater income inequality. That's one phrasing of it. Ew, that's not the correct phrasing, I just said it. But so you got to read carefully if they're talking about inequality or inequality, and I wrote the wrong thing. Greater income inequality. Which could be rephrased. So it's going to be, you got to read carefully, and a lot of times when I see these phrases, I got to like stare at it for a little bit and make sure I know the interpretation or what it's saying. Greater income inequality, bad, you know, the 1%ers are controlling too much money, or less income equality, which is the same thing. Things are not really equal. I'm not making any judgment about that, but I'm just making sure we can interpret these phrases related to a Gini index, and higher Gini index means you have less equality. All right, so let's do one of these. Calculate the Gini index, and it's most often used for countries, the Gini index of a country or an entire nation. It could be done with particular career fields, and that's what the example that I'm going to work with an example that's that. The homework problem that I gave you on this will be comparing 3 different professional sports and their income inequalities within their players. You'll see, but so you have 3 of them to work with. We're just going to do one. Jump to the Gini index. This is fake, by the way. Medical doctors. If the Lorenz curve is L of x is equal to 1/3 x cubed plus 2/3 x. Okay, and we're just going to follow this formula, but it is sort of good to know what it is. But from here on out, let's just do the formula. Okay, so we're going to come to the Gini index. G is equal to 2 times 0 to 1. And it has to be a function, by the way, that passes through 0, 0 and 1, 1. So you can't just make up any function as a Lorenz curve. It has to make sense, and for it to make sense, it has to have those 2 properties. What am I doing here? Oh, I'm integrating. Not just this function, make sure we're aware of that. But we're integrating x minus that function. It is a region between 2 curves. The upper curve is always that. The lower curve varies from problem to problem, or basically career field to career field, or nation to nation. Okay, I'm going to combine like terms and distribute that minus sign as well. I'm going to have negative 1/3 x cubed, and then I'm going to be subtracting 2/3 x, so that'll be plus 1/3 x. Okay, I'm going to do my antiderivatives now. It's going to be negative 1/12 x to the 4th plus 1/6 x squared. I'm evaluating from 1 to 0, and that whole thing is going to be multiplied by 2, so that's how I write that to show the steps that I have to do in the future. The usual antiderivative, my bounds there with a vertical line. I don't know who came up with that, but that's what they always do. And once I plug it in, I'll plug in 1 in there, I'll plug in 0 in there. I can tell that plugging in 0 there will just get wiped out, so I'm going to not write that this time. And then I'll multiply the whole result by 2 to get the accurate Gini index. And I'm going to do it over here. Shouldn't be that bad. It's actually, you know, computationally it's pretty nice because you've always got, it's oftentimes powers of x, and you're always going to be plugging in, doing from 0 to 1, so 1 to any power is just 1. I want to write it out formally in 0 for that second piece when I'm plugging the antiderivative, and that whole thing multiplied by 2. So to be clear, I plugged in 1 into that antiderivative. Oh, I forgot to square the 1, although it doesn't matter. And then I plugged in 0 into that antiderivative, but I knew it was going to just be 0 anyway. And I'm going to multiply the whole result by 2. I don't know if I should do the 2 first or the common denominator first, but common denominator is fine. It's going to be 2 12ths minus 1 12th. It's going to be 1 12 times 2, 1 6, and I work it out, 0.167. Okay. No, it will be less than 1. What am I talking about? Okay. That's your Gini for medical doctors, and I had a follow-up question, but I don't know where I want to go. I'm going to go over here. I'm kind of disorganized. Follow-up question, because your homework will have you compare and discuss which one has the most inequality and the least income inequality. So be careful of the phrasing, and I'm just going to do one example of that. That's medical doctors, the Gini index of medical doctors, supposedly. Suppose lawyers have a Gini index of, I'm not going to make you do another one, this is pretty straightforward, but let's say they have 243. And now we have to watch this phrasing here. Which group, lawyers or medical doctors, has, here's where we got to watch the phrasing, less equitable income distribution. Equitable means fair and equal. This is less equitable, less fair. And I think I borrowed that phrasing from the homework assignment so that we could look at it in the notes and grapple with it together. All right. Medical doctors are this. Lawyers are that. Lawyers have the bigger Gini index. Bigger Gini index means you got a bigger banana slice, which means that that's worse for equality, income equality. So higher Gini index is less income equality or greater income inequality. Read that carefully. I know. Anyway, let's make sure we know what we're asking. Less equitable income, less fair, so more unequal. And the higher one is more unequal. So which one has less equitable? Well, which one is less fair? Lawyers. Medical doctors, they all go to medical school and they, then they work in a hospital and they maybe do their private practice. Lawyers, and this is relatively true. These are not accurate, but it really is true that lawyers, sometimes they can work for a large corporate firm, but a lot of times they get stuck if they're on the bottom of their graduating class and do poorly in the bar. They get stuck doing public defenders for a while, and it's just not very well paying, very hard work. And I've known a lot of people that went into law and they regret it because it wasn't as lucrative as they thought. I don't know any doctors though. But anyway, yeah, so lawyers, according to this, has less equitable income distribution, which means that there are lawyers working for corporations that make bank, and there are some struggling to get by. All right, anyway, that's the example that I want you to do on for related to this. Then I'm going to put on the exam, and I'll put on the next quiz, the quiz for this section.